So the equilibrium constant is a way to quantify the concentrations of reactants and products at equilibrium. Here we have our generic chemical equation with the coefficients as lowercase letters and the capital letters as the chemical formulas. And this is the definition, essentially, of the equilibrium constant. So what we have here are the products divided by the reactants. And if you remember what delta is always final minus initial. This is kind of like that. It's the products, the final thing, over the initial thing. So it's the products over the reactants. And we have the molarity, the molar concentration of each substance, raised to an exponent, which is equal to its coefficient. So we have the concentration in moles per liter of C raised to the C power. And here we have the concentration of D raised to the D power. And those are multiplied. And then we divide by the reactants. So here's another place where it can get confusing with these letters. So capital K that's not italicized is the abbreviation for Kelvin. And the italicized capital K is the equilibrium constant. Right? Not confusing at all, right? Then lowercase k is kilo. So in typed things, variables are given, their symbols are italicized. K here is an abbreviation for a unit, Kelvin, and units are not italicized. I will not try to trick you with that, but just something to watch out for. This is not Kelvin is equal to these things. So this is also known as the law of mass action. Okay, so according to the law of mass action, which is the correct expression for the equilibrium constant for this reaction? So there are different approaches on multiple choice questions. I think sometimes it's better to just find the answer yourself without looking at the choices. Because sometimes when you look at the choices, you're like, oh, wait a minute. So let's just not look at the choices. And what we just learned about the equilibrium constant, what are we supposed to do here? So the equilibrium constant is going to equal something over something. Which goes on top, products or reactants? The products. So we have one product here, and so that's the concentration of C. And what do we do with this coefficient? That's the exponent. And then we're going to divide by the concentrations of the reactants. So A and B. And the A needs to be squared, right? Because of this. Because of this too. So then we look for the one that matches up, and it's D. Any questions? This idea of raising the concentration to the exponent is the same as what we saw in writing rate laws for elementary steps, right? And so it's just this really nice pattern that we can follow. Products over reactants, the coefficients become the exponents. Any questions? So, applying the law of mass action to a balanced chemical equation. So here we have an equation, chemical reaction, and so K is equal to the concentration of the products, so NO2 raised to the fourth power, times the concentration of oxygen, divided by the reactants, here N2O5, squared because it has a coefficient of 2. Okay, so the coefficients become the exponents. Express the equilibrium constant for the combustion of propane as shown by this balanced chemical equation. So K equals what? My concentration of CO2 to what power? To the third power times the H2O to the fourth power divided by the first reactant, exponent of 1, coefficient of 1 that's not written, and so exponent of 1, also usually not written, O2 to the fifth power. Any questions? So the meaning of that equilibrium constant. When the equilibrium constant is large, and by that we mean a lot bigger than 1, in this context, 10 would be considered to be pretty close to 1. So when we're talking big, we're talking really big, like 10 to the positive 19. There are some equilibrium constants that are like 10 to the plus 30. Really, really big. So when K is large, that means that the numerator must be bigger than the denominator. The concentrations of the products must be larger than the concentrations of the reactants. Does that make sense? So if K is a large number, it means that the reaction goes further to the right. It makes a lot more product and it uses up a lot of the reactants. We need to be able to remember K is large favors the products, K is small favors the reactants. And that's one of so many things in chemistry where you have two concepts linked to each other, and it's really easy to get them backwards, right? So the way I remember this is, I just stop for a second and think about it. Well, if this is big, then this must be big. That's the products. Big K favors the products. A small k, much less than 1, here in this example is 10 to the negative 31, really, really small, indicates that the reverse reaction is favored. So here we look at k. If k is a really small number, that means the numerator is very small and the denominator is very big. So with an equilibrium constant like this, hardly any of the product is going to form. The equilibrium constant, though, says nothing about how fast a reaction gets to equilibrium. It could happen in the matter of seconds. It could take years. The equilibrium constant says nothing about that. So, summarizing the significance. K is very small. A reverse reaction is favored. Doesn't go very far. There's a lot of reactants present at equilibrium. K is very large. The forward reaction is favored. It essentially goes to completion. We're not going to say it does go to completion because if there's even like two reactant molecules left, is it complete? No, it's not. But essentially, for all practical purposes, it may be. And then when K is approximately 1, which, is probably like 0.001 to 100 or something, compared to these other really, really big numbers, then neither direction is really favored, and it's going to just be about halfway. So consider this reaction, and again, they're using colors instead of shapes. We have red circles and black circles. And so we have this equilibrium at 3 different temperatures, and it's asking us at which temperature is the equilibrium constant the largest. Consider this reaction, and we're asked at which temperature is the equilibrium constant the largest? What's going to be true when the equilibrium constant is large? More products or more reactants? More products. So which of these temperatures has more products? C. Here we have a lot of products and very few reactants. Any questions? The equilibrium constant for the reaction A goes to B is 10. A reaction mixture initially contains A of 1.1 molar and B of 0 molar. Which statement is true at equilibrium? The mixture contains A of equal to 1 and B equal to 0.1. A is equal to 0.1 and B is equal to 1, or equal concentrations. Well, this is K. So K is equal to 10, and the equilibrium constant equals the products over the reactants, right? So the product is B, divided by the reactant is A. So this is a conceptual problem, and so we shouldn't need our calculators. Which is bigger, B or A, for this to be 10? B has to be bigger. So then we can choose this choice where B is larger than A. They're not going to be equal. They would be equal if the equilibrium constant was 1. Any questions? Okay, we're going to look at some relationships between the equilibrium constant and the chemical equation. And this is a little bit like when we talked about Hess's law and delta H's. And if you reverse the reaction, then you change the sign on delta H and things like that. If you doubled the reaction coefficients, then you multiplied H by 2. So this is similar, except it's exponential. So if we reverse the equation, here we have A plus B going to C. If we reverse the equation, now we have C going to A plus B. We invert the equation. Instead of changing the sign, which would be multiplying by -1, this is essentially raising it to -1 power. So let's see how that works. In the forward direction, we have C cubed divided by A times B squared. Okay. When we look at the reverse reaction, we have A times B squared divided by C cubed. So this, we turn it upside down and we get the reverse. That's the same as raising to the -1 power. It's doing the reciprocal. So reverse the equation, invert the equilibrium constant. If you multiply the coefficients by a factor, you double all the coefficients, then you raise the equilibrium constant to the same factor. Again, instead of multiplying like we did with enthalpies of reaction, we're going to raise to the power. So let's look at this again. So here we have A plus 2B equals C, and so our equilibrium constant is going to be C cubed over A times B squared. Now over here, we're multiplying all the coefficients by some number n. It can be 2, 3, whatever. So we're calling this K prime because it's not exactly the same. So this is going to be C raised to the 3n power. divided by a to the n power times b to the 2n power. This is equal to c cubed over a times b squared to the n power. Any questions? If you add two chemical equations together to get an overall equation, with delta H, we added the delta H's. This is one step up mathematically. We're going to multiply the equilibrium constants. And this pattern of multiplying by -1, raising to the power of -1, multiply by some number, raising to the power of some number. Here, instead of adding, we're multiplying. This is just a pattern that I observed that helps me remember what's happening here. So A goes to 2B, here's our equilibrium constant. And B goes to 3C, there's the equilibrium constant. If we add these two equations together, this is forming 2B, and then the 2B is getting used up, right? So when we add them together, we're going to get A is in equilibrium with 3C. So let's call that K3, and that would be C cubed over A. And that should equal K1 times K2. So K1 is B squared over A, and we're going to multiply by C cubed over B squared. The B squareds cancel out. C cubed over A. It seems like some kind of weird magic. It's just math. Can I send you that slide? Yeah, I can. Okay, so let's test that. The reaction A goes to 2B has an equilibrium constant of K equals 0.010. What's the equilibrium constant for the reaction of B going to 1/2 of A? So we need to ask ourselves, how did this chemical reaction change? What was done to it? There were two things that happened. Here A is a reactant, and here A is a product, right? So the reaction was reversed. So then what do we do to the equilibrium constant if we reverse the reaction? We don't multiply by -1, we raise to the -1 power, or do the inverse. You could also write that as 1 over 0.010. So, reversing the direction of the equation, we take the equilibrium constant and raise it to the -1 power, which is the same as 1 over. That makes sense? Okay, then what else happens to get to this? How do I get from A to 1/2 A? Multiply by 1/2. Divide by 2. Multiply by 1/2. So from here to here, I've multiplied the coefficient by 1/2. And over here, I've multiplied the coefficient by 1/2. So what do I do to K? I raise it to the 1/2 power. And so I guess, it becomes kind of a mess over there, right? Oh, I accidentally tapped on it and gave us the answer. So then we've got 1 divided by 0.01, which is 100, and something raised to the 1/2 power is the square root. You can also do it on your calculator. You can raise it to the 0.5, or 1 divided by 2 power, and this is going to give us 10. Any questions? It's just like a not very popular game that you have to learn how to play, and it's got 3 rules. You guys are quieter than you were on Monday.
It's hump day.
It is hump day. It's true. Okay, let's practice this one. Manipulating K to reflect changes in the chemical equation. Consider the following chemical equation and equilibrium constant at 25 degrees C. So here we've got this equation, and this is what K is equal to. At the same temperature, what is the equilibrium constant for this guy? So this is just like the previous problem, except it's a little more complicated because instead of A and B, we've got chemical formulas. We've got 2 reactants or 2 products, right? So what happened to get this equation to that equation? We've got it multiplied by 2. Yeah, because this here, COF2 was multiplied by 2, and here it's multiplied by 4. These both had coefficients of 1, and now these are coefficients of 2. So what we've done is we multiplied by 2, and so that means we do what to the equilibrium constant? Raised to power of 2. What else did we do? This is a reactant, and now it's a product. We reverse the direction of the reaction. So reverse the direction. What do? Flip it. We'll invert K, which is the same as raised to -1. So what we need to do is we need to invert the equilibrium constant. So that's going to be 1 over the equilibrium constant, 2.2 times 10 to the 6th. And we need to square it. Times 10 to the 6th. I get 2.1 times 10 to the -13. Anybody else get that? 2.1 times 10 to the minus 13. Any questions?
I have a question.
Yeah.
I don't know if I wasn't paying attention or not, but is the temperature like useless information?
That's a great question. Is the temperature useless information? Why are we given the temperature? The temperature is not useless, but we don't need to use it.
Yeah.
So the reason it specifies the temperature is because just like a rate constant, equilibrium constants also often change at different temperatures. So here they're just saying these are at the same temperature. If this was a different temperature, we couldn't do the problem without more information. And so it's one of those things that they tell you that you don't even realize you need. If they don't say anything about the temperature, they're not saying that it changes, then you kind of just have to assume that it isn't changing, but they're just dotting their I's. Other questions? Predict the equilibrium constant for the first reaction, given the equilibrium constants for the second and third reactions. This looks like a good exam question. Unfortunately, you don't get to choose. So how do we approach this? We have to figure out how can we combine these two reactions to get that reaction. And again, this is very much like the Hess's law stuff that we did in Chem 1A, which you probably didn't like.
Isn't the thingy where we like multiply it by different numbers to make it equal the same on both sides? Like when you add them all together, expressions together?
I think you're thinking of balancing redox reactions. Yeah. Sometimes this involves multiplying, but it'll involve just multiplying one equation or the other one. So this is the approach I use in teaching Hess's law. I'm just going to kind of color code these things because it's easy to get them all confused. Right? So I'm going to make hydrogen red. Let's make the water blue because water's blue. And let's see, carbon monoxide can be orange. And methanol can be purple.
Did you know if you do the thingy and then you hold it, it makes it straight?
It does that on a lot of things. It doesn't do that on this program. Yeah, it's a bummer. But I can make shapes. Oops. I can make squares. And I can make circles or ovals. So that's cool. I can make a straight line if I choose the straight line button. Yeah. So we need to combine these two to get that. So let's just start with the first one, right? The CO2 is a reactant in our desired equation. Let's look for CO2 in these two that we're going to manipulate. Well, it's a product. So let's start by writing this equation in reverse. So CO2 plus H2 in equilibrium with CO and H2O. And I'm just going to highlight those again. So now we've got CO2 as the reactant, which is what we want. So we took this equation and we reversed it. So then K for this new reaction, maybe we'll call this 4.
Is the inverse?
It's the inverse. right? So that is going to be 1.0 times 10 to the 5 to the negative 1 power, or 1 divided by 1 times 10 to the 5. And, you know, it might be just less confusing to just write out what that is. That's going to be 1.0 times 10 to the negative 5. Okay, so we got this guy taken care of. So the next one, H2, okay, so we have some H2s here, but we need to have 3 of them. If we multiply this by 3, it's going to mess up the CO2, so that's not going to work. So we're going to have to bring in some more. Well, here's 2 H2s. So if we put that in there, then those will add up to 3. So let's do that.
I have a question.
Yeah.
How is H2O graph G instead of L?
Because it's hot.
Gas.
Yeah, it's a good question. Why isn't the H2O a liquid here? Because it's warm. Okay, so we're going to take that bottom one and just copy it down. I put my arrows in first because it's just so much easier if your arrows are lined up. And then over here, I've got CH3OH. Bless you. Okay. Did I do anything to that equation? Did I change it in any way? No, I didn't. So nothing happens to the equilibrium constant. It stays the same as it was before. So I've got CO2 and I've got 3 H2s. The reactants look like they're lined up. So let's just add them together and see if we get what we want. So CO2 plus 3 H2. This one doesn't show up in our desired equation, but here it's being formed and destroyed, and so it goes away. Do you see what I did there? If you don't write things down, it can get really, really confusing. And all these letters in here, and like there's C's and H's and O's everywhere. And 2's and 3's, and sometimes the only difference, like here, this is CO2 and that's CO. Could you mistake those for each other? Sure, you really could. So, you know, if you like colored pens or on your tablet, you can highlight, right? What if you're just using paper and a pencil and you don't have colors? Well, you could say, well, I'm going to let this be equal to A, and I'm going to call H2 B, and this is going to be C, and H2O is going to be D, and you could write yourself a simplified equation to do all the rearranging, right?
Or you can get highlighters or color pens from the dollar store.
Or, yeah, you could get highlighters.
On the budget.
Yeah, you could get some highlighters or colored pencils. Okay, so we added these together. What do we do with the equilibrium constants? We're not going to add them. We're going to multiply them. So they're calling this K1, right? And so this is that equation. K1 is going to equal K4 times K3. So 1.0 times 10 to the minus 5 times 1.4 times 10 to the 7. it's plus 2. Any questions? You definitely should be able to do a problem like this for the exam on this chapter. Okay? 140.